The next speaker is Krishna Sarvani Desabhotla. You can now share your screen. The title of the extended abstract that was accepted and now presented is Automation Process of 3D Scan-Based Exoskeleton Brace Design. Please go ahead, Krishna. You're still muted.
Can everyone see my screen?
Yep, perfect.
Okay, perfect. Good morning, good afternoon, good evening, depending on where you are in the world. My name is Krishna Sarvani Desabhotla, and I'm from the Laboratory for Non-Invasive Brain-Machine Interface Systems at the University of Houston. I wanted to start by thanking Dr. Su and all of the organizers for putting this workshop together. I've already learned so much today, and I'm really looking forward to the rest of the presentations. Today, I'm going to be discussing the various iterations of the brace design for our customizable pediatric exoskeleton, as well as our current work with automating this process. Cerebral palsy is the leading cause of mobility issues in the pediatric population. And despite the increasing use of robotics in gait rehabilitation, there are limited pediatric options. The idea to create a customizable pediatric exoskeleton with the future integration of EEG and EMG multimodal signaling was inspired by the fact that early interventions could really help improve the quality of life for children suffering with mobility issues. This was our first design iteration for our customizable braces. The first step in this process was to 3D scan an individual's lower limbs, and from those scan dimensions create a foam mold, as well as a 3D printed ABS plastic embedded framework. We then used carbon fiber cloth to line both sides of the frame, and after adding epoxy, curing, and trimming, this was our final result for a shin brace. Now, this process was great because the 3D scan dimensions made it more accurate than using simple manual measurements. However, the process took a long time, and the use of external carbon fiber layers and the epoxy could reduce the form-fitting nature of the brace. Because of these considerations, as well as the decreasing cost of 3D printing, we made the decision to transition to an entirely 3D printed brace. Now, because we were 3D printing the brace in its entirety, we could create the brace directly from the scan in SolidWorks. And this was ideal because it was as accurate to the scan as possible. This also allowed us to have space for increased breathability, as well as create structural reinforcement into the brace itself. On the right is our fully assembled, customizable pediatric exoskeleton prototype with our braces incorporated. Now, this process was still quite long. It took about 5 to 6 hours to create a complete set of braces based off of the scan. And because we had to create the brace from scratch every single time, this would make it harder to standardize our brace design across various users. This wasn't ideal because we want our exoskeleton to grow with a child. So we would have multiple 3D printed braces throughout the course of a user's childhood. Because of these considerations, we decided to try and create a template brace that could then transfer from one scan to another and readjust and reorient itself automatically. That's design iteration 3, and it's our current work. As you can see here, we've created a proof of concept brace that uses static variables for the connective elements, so where the brace connects to the rest of the exoskeleton, dynamic variables for the rest of the design elements so that the design elements readjust themselves to the size of the new scan. We also use joint points. So in this case, we use the hip joint to help with proper reorientation as the brace transfers. So this is the brace transfer process. The first thing we're doing is just turning scan visibility off so that we're only working with our reference surfaces. We're changing the reference surface that the brace is based off of from the gray scan to the white one by redefining the edges that it's based off of. We also had a plane in this model that was based off of the hip joint for proper orientation, so we're correcting that for the white scan as well. As you can see, we've shortened the brace creation time from a few days in design iteration 1 to a few hours in design iteration 2 to currently, with this proof of concept brace, it's only a few minutes. We're currently working on finalizing the brace design. by defining it using the guidelines that I mentioned with static and dynamic variables, as well as joint placement. And we're hoping to keep the total brace creation time under 10 minutes. In the spring, after bench testing is completed, we're going to do healthy subject testing with a small cohort and then feasibility testing with the clinical population afterwards. Thank you so much for your time. If you have any questions or would like to learn more, please contact me at this email. Thank you.
Great. Thanks a lot, Krishna.